In this lesson, we will look at graph behavior, intervals on which a function is increasing, decreasing, or constant, and maximum and minimum values. Definition of increasing function. Suppose f is a function defined on an interval I. We say f is increasing on I if and only if f of a is less than f of b for all real numbers a and b in I, with a less than b. Let's look at a graph. On this graph, the function f is increasing on the interval from -3 to -5/4, which on the graph would be right here. For all points a f of a and b f of b on this interval, and let's pick a couple here. We can see that where a is less than b, f of a is less than f of b. So by the definition, f is increasing on the interval, the closed interval from -3 to -5/4. F is also increasing on the closed interval from 5/4 to 3, right here. Let's look at intervals where a function is decreasing. The definition of a decreasing function. We say f is decreasing on an interval I if and only if f of a is greater than f of b for all real numbers a and b in I, with a less than b. So this is almost the same as increasing, except that f of a is greater than f of b here. Looking at the same graph, our function is decreasing on the interval from -5/4 to 5/4. And it is also decreasing on the interval from 3 to 5. Let's look next at the definition of a constant function. The definition is very similar to the two definitions we've just looked at, with the exception that f of a is equal to f of b when a is less than b. If we look at the graph again, we'll see there are no constant intervals on here. A constant interval is like a horizontal line, would be an example of a constant function. Okay, definition of local maximum. A function f has a local maximum at the point a, b, where b equals f of a, if and only if there is an open interval I containing a for which f of a is greater than or equal to f of x for all x in I. Okay, so here is an example of a graph that has a local maximum at the point 1, 2. There is an open interval of x values here. So this is our x value of 1. There's an open interval of x values containing x equals 1, for which f of 1 equals 2 here is greater than or equal to our corresponding y values, our f of x values. Okay, we can actually say here that there's a local maximum at the point 1, 2. The local maximum is defined to be the y value, y equals 2. Similarly, we'll look at the definition of a local minimum. The difference here is that f of a is less than or equal to f of x on our interval. And if we look at a graph that contains a local minimum, the local minimum will occur at the point -1, -3. The local minimum will actually be y equals -3. Definition of absolute maximum. The value b is called absolute or global maximum of f if b is greater than or equal to f of x for all x in the domain of f. On the graph that we've been looking at, we can see that we have an absolute maximum right here. The absolute maximum is going to be y equals 4. Absolute maximums are a little bit easier to find. They're just the highest point on your graph or the largest value of y that occurs. Definition of absolute minimum, about the same as for absolute maximum, except here we're looking for the value b, where b is less than or equal to f of x for all x in the domain. And so here, the absolute minimum, the smallest value on our graph, is going to be right here at y equals -4. So y equals -4 is our absolute minimum. Notice that that y equals -4 does not happen to be a local minimum, but it is defined to be an absolute minimum. Try this last problem on your own. Sketch the graph of a function that has a local minimum at the point 1, -1, local maxima at the points -1, 0, and 2, 2, and an absolute maximum at 2, 2, and absolute minimum at -3, -2.